Hello everyone, thank you for joining us today. Today we'll have a talk on the assessment of reservoir mechanical robustness in geological carbon sequestration. Our guest speaker today is Ms. Zhidi, our Vice President of the ARMA student chapter at the University of Utah. Ms. Zhidi is a PhD candidate in the Department of Civil and Environmental Engineering at the University of Utah. Her dissertation focuses on the coupled hydrochemomechanical process in subsurface CO2 storage sites and multi-scale geomechanical properties. She has 7 years of experience performing flow-through experiment and a variety of experiences with geomechanical tests across micro to macro scales. Ms. Wu holds a bachelor in geology and a master of science in hydrology, both obtained from New Mexico Tech. Throughout her graduate training, Ms. Wu has built and modified high pressure and high temperature flow-through systems and designed a series of fluid rock interaction experiments for a specific research objective. Her interdisciplinary research interests also include batch, reactive transport, hydromechanical numerical simulation, and uncertainty quantification. Ms. Zhidi, thank you for joining us today, and the mic is yours.
Okay, thank you. Yeah, thank you, Omar, for the introduction. Hi, everyone. So today I want to talk about the assessment of reservoir mechanical robustness in geological carbon sequestration. So, and then just give you a preview. These are the CT scans of pre and the difference between pre and post the flow-through experiment. And these are the flow paths that we observed in our data. So, and then so I want to outline my presentation into these sections. First, I want to talk about the general geological carbon sequestration, the concept of it, and what is the impact of the GCS on the reservoir robustness or the reservoir mechanical properties. Third, I want to dive into a little bit more detail on the mechanical modulus, talk about the dynamic and static mechanical properties, and because in a case study we'll have a lot of observation on them, so I want to bring it up front. And then next to that, I want to also talk about the controls on the mechanical modulus itself, also in preparation for this case study introduction. And then the fifth section is, I think, the most interesting part of the presentation is to talk about a case study that me and my colleague at New Mexico Tech, and it's a team of work of across 7 years of time span on a case study at a CO2 EOR site at Fort Worth Unit, Texas. And then I'll conclude my whole presentation with the summary. So why geological carbon sequestration? I believe we all have a sort of understanding of what is carbon sequestration. Basically capture the CO2 from the air or the point source and then inject them into the subsurface, thousands of feet deep, and then store them permanently, hopefully for thousands of years, even longer than that. So this is a general picture of how the geological carbon sequestration project or a site will work. So first of all, these are the four elements that's critical for enable to run the carbon sequestration. First, you need a storage resource. So it's either usually close to a plant, could be a coal plant, could be industrial petroleum platform, like a well site, and or injection, like a groundwater injection site. So, and that's, or or direct air capture, but we won't go that in very, very deep. And the second element is injectivity. So that's the rate of CO2 we want to inject into the subsurface. And the third is integrity. So integrity is basically a way, so we want to permanently store the CO2 into the subsurface. So a seal or multiple seal layers of seal formations are needed for that to happen. So in this case, we have a saline aquifer, and then on top of it, there's a low permeability seal on top of it, so that it prevents the CO2 migrate upward. And they also have another example is a depleted oil reservoir. So it's another example, and then below and above it, we have a shale layer, plays a seal formation. Or we can also inject the CO2 in a coal seam bed, so that, and then also below and above it has low permeability seal formation. So that's another critical element for CO2 storage. And then the last one is the depth. So the depth of where we want to inject CO2 pretty much creates the environment that the CO2 will stay. So that determines what's the temperature we want the CO2 to stay, and the pressure also at that certain depth. So usually we want CO2 to stay in the supercritical phase. So that's above about 35 degrees C and 1100 PSI. That temperature pressure range above that critical point. So, and usually the depth that we inject it at is above that pressure temperature point. So then enable the CO2 stays at supercritical phase, low volume, so that maximize the storage capacity. Also, I want to talk about the driven force, the drives for the whole society and the commercial or the industry to do this project, to store the CO2, to do this geological CO2. So 45Q is it's a policy that's released, I believe, in 2018. It's pretty much specifically in the US, so enable people to purchase the right to emit the CO2 or sell the right to allow people to emit CO2. So basically, we used to emit the CO2 from the plant for free without any permission, but right now, apparently, we do need to purchase a permission for that. And that places a bar for the industry that you need, before you do anything, you want to engage the budget on how much CO2 you want to emit to the atmosphere, because we want to mitigate the climate change. We want to reduce the CO2 in the atmosphere. And then the neutral carbon neutral is another agreement that kind of like a lot of countries sign up for this agreement that reaches the net zero by 2040 or 2050. So that's an agreement that worldwidely. So not only just US, a lot of other countries are actively participate in reaching this goal. And then another driven force, recently, I also just learned this news that the Rocky Mountain, one of their coal plant is going to, they're going to postpone their closure until 2042. So it means that we have to, for some reason, for the policy reason, the big picture, people have to burn the coal or to burn the fossil fuels longer than we expected. So it means that more CO2 would be generated from the plants, which also means more need of storage the CO2 into the subsurface. So it's even becoming more critical. And that coal plant that's not the only coal plant that's postponing the closure. There are many coal plants around the U.S. Is postponing their closure date, and also or postponing the opening of a nuclear plant. So So the setback of renewable energy and continued use of fossil fuel really puts a high demand on geological carbon sequestration. Okay, and let's talk about the impact of geological carbon sequestration on the reservoir mechanical properties. So what will happen? Let me ask you a question first. What do you think the CO2 will, how much integrity degradation, like how much weakening of the rock you think this in CO2 injection will cause on these 4 scenarios? And then, so the first scenarios, the 4 scenarios describes the cement textures. The first cement textures is more disseminated and more sparse distributed, and they're placed within the pore space. The second one is a nodule localized cementation, and they kind of forming around the core, forming around the grains as a nodule in a nodule shape, just like what's in the shade. And then the third texture is like a laminated kind of texture of cement going around the grains. So the cements are the gray color. And then the last one is a very pore filled, like a fully filled in the pore space, those cements. So if I ask you a question, by dissolving same amount of cement, which scenario will see the most significant mechanical degradation? By saying mechanical degradation, that's a really good example. So stress strain curve, the slope is like the Young's modulus, and then the blue one is before the CO2 injection, the red one is after, and apparently the slope drop means that the mechanical property decrease. So which rock is more likely to experience that conceptual model?
It's straightforward.
Yeah, perfect. You passed the quiz. That's right. So yeah, the conceptual model pretty much what I want to convey here is the more stronger the cement is playing a role on supporting the structure, the more likely the destruction of the cement will lead to more mechanical degradation. Because here, no matter if you take out a couple grains of cement, it won't cause too much a difference for the structure, because the cements are already very crumbling, distributed in the pore, but not the other one that's pretty much like glue the rocks together. Yeah, that's the whole point. And there you go. From the low impact to the significant impact. Yeah, and the case study I will talk about, the rocks, they have this type of texture and the fourth type of texture. So that's something that you can anticipate the results in the case study. So, and then I want to talk about dynamic and static mechanical modulus. So shift the focus a little bit. When Carlos was presenting last month, he mentioned about dynamic and static mechanical moduli, as you guys remember. Oh, no, he mentioned about the dynamic elastic moduli. I remember a lot, which is this P wave and S wave. So the difference between dynamic and static moduli is that dynamic moduli calculated from the elastic wave velocities, I mean the VP, VS, and the density. So you guys probably already very familiar with that. So the Poisson ratio and Young's modulus are all function of VP and VS and the density. And the VS and VP, they are the primary wave and shear wave transferred through the rock. So that's how the physics of dynamic elastic test work. And then the static moduli I calculated from deformation, the actual deformation measurements. So, for example, you guys must be very familiar with this already. So you either compress a rock or you break break a rock apart. So in this case, you compress a rock, and it has a deformation in axial direction and a radial direction. And then the Young's modulus would be stress over the axial deformation, axial strain, and Poisson ratio is the negative of radial and axial strain. So it's from the direct deformation strain. So what's their impact on magnitude? Which one do you think, are they always going to be the same, like the Young's modulus calculated from these two measurements and the Poisson ratio, specifically Young's modulus? Do you think they all always be the same, or one is always larger than the other one?
So the CO2 will have a chemical reaction with the cement, and will cause some pores inside, and will reduce the Young's modulus.
Yes. But the question, yes, you're right. The question, that's the point that I will talk about in the next session. Right now, I'm just simply trying to differentiate the difference between the two, and what's one featured for, what's the other one, like what's the difference between the two measurements in terms of the deformation. Do you expect the Young's modulus measured from dynamic tests will be larger, or do you think the Young's modulus measured from static tests will be larger? And larger? Okay, we have one vote for that. You vote the other?
I'm thinking about the state.
Okay, Eileen, do you have a?
Okay, so if there's more strain, then it's going to be smaller, right?
Yes.
Okay.
Because more strain, more deformable, and then it's yes.
Okay,
lower.
so I think dynamic will then be smaller because it's over a larger area.
Right. Yeah. You got the point. Yeah, you got the point. Perfect. So it all depends on the strain, right? Or the displacement, how much it changes in length. So according to the literature review, the strain or the magnitude that usually happen in dynamic tests by those waves, it's 10 to the -7. And then the strain of the magnitude of the strain of static tests can reach up to 10 to -2. So 10 to -7 versus 10 to -2. Hold on, sorry. Okay. Let me check one thing. Static is -2. So if we say, hey, can you see me? Static is -2, dynamic is -7. So dynamic tests experience much less deformation. So dynamic has much larger, not much larger, but usually, generally, larger Young's modulus than the other. So that's it. Although it's not always the case. It also depends on the rocks. Depends on if it's a granite, if it's a metamorphic, if it's a sandstone, if it's a shale. This is the study that I conducted in my chapter 2. And here, if you just look at on your right, so static Young's modulus as a function of dynamic, and the black dashed line is a slope of 1. So and I fit a linear regression onto those. So these rocks are shale, and all the other colorful colors, those are sandstone. So you see, for the shale, the slope is less than 1. So it means that the dynamic is larger than elastic. But then for the other sandstone, the regression is 1.36. So that means static is slightly larger than dynamic. So yeah, so again, rocks are heterogeneous, but for a specific type of rock, you can there usually a pattern on which one is larger or smaller. But in terms of the physics from my last slide, since there is less strain experience in the dynamic, their Young's modulus tends to be higher generally. So most of the rock, I guess, will following the trend of this regression.
So these results are out from the sandstone.
These black symbols, those are from shale. Those are from an unconventional reservoir. All the blue, purple, green, orange, those are sandstone.
So can you change the slides to?
Oh, that's a good point. Okay, didn't realize it's black swap use slideshow. Okay, that should work. Got it. Okay. Thank you, Omar. Do you have more questions on this?
In terms of comparing between dynamic and static models, which of them is more representative to actual stress status on the reservoir?
Okay, I think it's static Young's modulus, just because it's a more direct measurements. It's measured from, the actual deformation of the rock. Because when you do the static Young's modulus or static mechanical tests, it's more similar to what's really going on in the subsurface, and also that's a test that people usually do for the wellbore instability test. And but although it's hard to get access to them because you have to take the rock out and then really do the test on them, while dynamic test, you can do it from the surface. Just just do the wave propagation. But I think most literature or what the textbook was saying that static Young's modulus is more representative. Yeah. Okay, controls on the mechanical modulus. Yeah, so we kind of talk about these two types of different mechanical modulus, and then what are the properties or the factors that can affect mechanical modulus in general. So, and this is also concluded from one of my study is that, so you probably can't see very well, but I can walk you through. These are the impact factor plots, and impact factor plots of multiple models that I generated. And I have porosity, I have clay content, which is the chemical composition. I have permeability. I also have the diameter of the sample. So that's some external factors. I also have FGC over CC. FGC over CC is the ratio between framework grain content and cement content. So that's another chemical composition factor. Basically, the harder parts of the rock over the softer part of the rock. And I also have MGS, which means the mean grain size. So it shows that the Young's modulus, or in this study, it says Young's modulus is most sensitive to FGC over CC ratio and porosity. Because the higher the bar, the larger the impact factor is. So, which makes sense. The porosity this is a conclusion that's agreed with a lot of previous investigation. Porosity really determines how easy or how compressible the bulk rock can be, and also that chemical composition also plays an important role in this. And this is the result of more detailed results of how Young's modulus will, as a function of all the rock properties that I studied, on a larger range. Most of them are nonlinear, I would say. So always give it a more thoughts, or give it a second thought on when you consider those control factors on the mechanical modulus, because you can't always assume them to be linear, and nonlinear is the key, and heterogeneity is the a contributor to it. Okay, now we can talk about the case study. So this case study is part of the Southwest Partnership, happened in Forest Once unit in Texas. So the field site, our core samples are collected from the panhandle of the Texas here, and then that's the Forest Worth unit, and that's the depositional history of the Forest Worth unit. It's located in the Anadarko Basin, and it has a fluvial depositional system. Means that it's mainly sands, has carbonate and clays are the main cement of the rock. And then this reservoir was originally developed for petroleum exploration, exploitation. They started to drill the well in the 1950s, and then they have some petroleum production. And then 1960s started to do the water injection for the more oil production. And then in 60s, they started to recycle CO2 injection for more petroleum production. Then 2020, after 2010, they started to do the anthropogenic CO2 injection specifically for the purpose of CO2 EOR. And that's when how the Southwest Regional Partnership happened. And okay, so this is a high pressure, high temperature flow through system that I've been doing this flow through experiment on. So they're all versions of high pressure, high temperature system, but they all share the common features that they always have a core vessel here to hold the core sample, and also and also around the core, either in an oven or with a heating band to provide this temperature supply, because this also has to happen in a high temperature, about 75 C environment. And also, they also have a few pumps that controls the pressure of the system. One pump is necessary for controlling the confinement pressure, and the other pump is necessary to control the fluid pressure or controlling the CO2 injection. A third pump is optional. It can do without that third pump. Right, and then some system, at least for our system, always have this fluid sampling line here so that we can collect the effluents. Right, so and that's the pressure that's the pressure and temperature we use for the system. And this is another example of a flow-through experiment setup. This is another one. This is the third one. The difference of this one, apart from the other two, is that this one has an axial. This one has a strain measurements. Axial strain measurements here. So not only you can do the flow through experiment, you can also monitoring the strain measurements when you apply the confinement pressure, or you upload, or you load or unload the pressure system. So we call this a creep flow through experiment. So for this type of flow through, we've done 15 experiments on that. For this one, we did 4 experiments, four samples on them. So that's 19 samples in total. And those 19 samples are all Morrow B samples that collected from the Farnsworth unit, and we categorize them into 5 rock phases, and then the different rock phases is featured by porosity permeability relationship and the lithology, which means like how big the pore size is, or where those pore located at, and the lithology, the chemical compositions of the rock. So there are five categories. So, and then this one is the categorization of those 5 rock phases. So they all share the same similar, not the same, but they all share the same diagenesis sequence. They all of them, we see quartz overgrowth, which is non-reactive component of the rock, formed very early in the history, like they formed first. And then other overgrowth precipitate, and then siderite cement starts, and there's some replacement happen, compaction, the overpressure environment, and some compaction of the formation happen. Then there's some dissolution happen, clay cement precipitation, and then there's finally this hydrocarbon emplacement where the oil forms, filling those pores. Okay, so after we've done, or during those flow-through experiment, we collect the effluents, right? So these are the results of the chemical components of the fluid during the experiment. For the calcium, so the takeaway message of I know it's a lot of information, but takeaway message of this slide is that we see dissolution of carbonates. And the carbonates that we have are the calcite, are the anchorite, are the siderite, so which contains calcium and iron and magnesium. So those are the main ones. And we see a lot of calcium increase. So the calcium concentration increase, also the iron concentration increase. And that means if we see those, it means there's a lot of minerals that contain those elements that has been dissolved. So yeah, we definitely see dissolution of carbonate cements, and we also see some iron concentration change. They increase and then they stabilize. So there are also siderite and chloride dissolution happen as well. Yeah, as for precipitation, we will see more. I think we will see more evidence of that in the XRCT images. So this provided evidence saying, oh, there actually dissolution happened in the rocks, and they are mainly carbonates. Yeah, same with the thin section data. These data provide the evidence that also reinforced our evidence saying that there is dissolution of carbonates, because these are the point count of thin section. So if you're focusing on clay, kaolinite, siderite, macropores, if you're focusing on the pores, macro means the macro porosity, or the porosity, the pore size that's big enough, or you can call it macro. Pre-test, post, and post. So the green color bar all slightly increased after the experiment. So it means that there are some pore opening occurred during the experiment. So dissolution. Oh, and this one shows what happened to porosity and permeability after the experiment. This is log permeability as a function of porosity, and the different, these background data point, those are the characterization data of porosity and permeability data of the entire formation. And so those are collected way before our project starts. So, and then people, like previous researchers, segregate them into 5 different hydroflow units, and then basically means the relations of permeability and porosity and the lithology, as I mentioned earlier. So in a solid or the post measurements, hollow symbols are the pre-measurements. So I have purple. Purple is the control experiment, so it means no CO2 has exposed to them. That's why the purple dots are really close to each other, because there's not much change in permeability and porosity happen. But for the blue or for the red data points, they tend to shift a lot compared to these background data points. They tend to jump from one hydroflow unit to the other hydroflow unit. So that means CO2 actually has an impact on porosity permeability, although we see more permeability change than porosity, because they don't shift a lot on the x-axis, but they do shift a lot on the y-axis. So like for example, this one, it shifts significantly. So, and that one is a carbonate. This is a calcite cemented sample. Means that there's absolutely a lot of calcite dissolved in that sample. Yeah.
For this, there is a blue tape that shows that there is a reduction in porosity in fact. With the triangle.
You mean this one or this
the
one?
other one, the top one. Yeah.
This one?
Yeah, this one.
This one.
Shows like there is a porosity reduction, right?
There is, so it's going from the solid or the post. So it's going from here to here. Yes, there is a porosity decrease. Yeah, and
however, there is a permeability increase. So.
Yes, so some rocks have permeability increase. Some rocks have porosity decrease, reduction. Good observation. If you look at this plot line enough, you'll see a lot of interesting observations, and this is one of them. So I can explain this. So the blue ones are disseminated carb. Disseminated carb here means they're mainly kaolinite, chlorite, ankrite, siderite. So those are the minerals that are less reactive than calcite, and they contains a lot of
Shale minerals?
I'm sorry.
Shale minerals or
Not kaolinite and chlorite, they're clay minerals. Ankrite, siderite, they're carbonate minerals. But chlorite and ankrite contains iron. So the blue data points, they're the minerals that contains more iron. So when iron carbonate dissolve or iron contained clay could dissolve, immediately after they dissolve, which I'll show you later, they tend to reprecipitate iron oxide, like hematite. So those minerals actually refill some of the pores. And we think that's the reason you see, that's the reason you might see the porosity decrease, because not only does dissolution, there reprecipitation happen immediately after, which there are evidence for that as well, which I will show you later. This is micro CT images of the difference in pore size of two samples. This one is the one that contains chloride, a lot of chloride. This one contains a lot of chloride and calcite. So as we saw earlier, calcite tends to dissolve more. So it makes sense this plot, the plot on the right tends to dissolve more, so that you see more preferential pathways. But this one's less. And they do form some dissolution, but those dissolutions are not connected to each other. So they're not big enough to create a new pathway so that the permeability will not be significant change in this one and that one. Okay, well, this is one, back to your point, like why some of the samples we see porosity reduction. So this one, hopefully it's good enough to see. This is one of the uncemented samples. So it's the sample that's lack of cement, but doesn't mean it doesn't have it. It still has some, just less. If we just look at the black and white images right now, the dark ones are the pores. So the different color refers to density, right? The darker the color, the lower the density is. So we see darker here, and then we see more darker area just above that. That means enhancement of macro pore. So that pore opened up a little bit means there are some clay dissolved, or there's some clay mineral dissolved. Even if this one doesn't have much clay, we think that the clay dissolved. But here, there are some lighter color mineral form here, and that's a new clay we found. So there's some clay dissolution, and then there's some clay reprecipitation, or even migration. You might be always there, you just with the flow, they change the location to the adjacent location. So we definitely see a reprecipitation of some iron oxides. And this plot shows is pretty much the difference between these two. And then just draw your attention to this white spot. This is where we see the precipitation. No, the dissolution actually. Yeah, so the white spot refers to the dissolution, right? Okay, so those are the results from the flow-through experiment. These are the results from creep flow-through experiment. So we add another element. You remember we have a strain measurements too. So that can give us some information about not only just chemistry, but also mechanical properties. These are the bulk modulus. From these strain measurements, we were able to calculate the bulk modulus. We didn't show about bulk modulus here because it didn't change much during the experiment. So that's why I'm showing the strains. There's not much strain happen. It's kind of always flat. So nothing too excited about the impact of CO2 on the bulk modulus. We just don't see much bulk modulus change during that creep flow through experiment. And here, same, we see here in the thin section, we notice something that even if in the control sample, the sample that without CO2 injection, we see some microfractures. So that indicate that those microfractures happened is not caused by CO2, is originally already occurred in the sample. Could be because of the compaction, could because of other something to do with the depositional history. So and the CO2 injection can actually prevent the weakening of the quartz. So it prevents the fractures to propagate more. So that's another interesting we found in the creep flow through experiment. P wave velocity. Yeah, this is another. So we're now shifting to more mechanical observations. P wave velocity, as we mentioned before, is a dynamic measurements. Here, we generally see P wave velocity decreased during the CO2 injection. Any point, all the points, most of the points are below on the lower region of the plot. So it means pre is larger than post, which makes sense. Well, there's some dissolution happen. The wave propagation might be slower now because of the microstructure change, which makes sense. But what we really want to have an explanation of these 2 points. Why they actually kind of got strengthened, and that has something to do with the reprecipitation or porosity reduction. So look at what these 2 plots data points correspond to. They are chlorite, so CHL chlorite, iron-rich clay, and this one is kaolinite. It's another type of clay. So pretty much. The rock got strengthened in terms of, slightly strengthened in terms of P wave velocity measurements. They are all clay or iron-rich clay cemented rock. not calcite or carbonate cemented. They're all here. They all experienced somewhat degree of dissolution. Maybe precipitation, but not the precipitation is not as much as we see in these two samples. Okay, then is the static mechanical measurements. So let's see what CO2 impact, how CO2 impact on tensile strength. So that's a type of experiment that we still compress the rock. It's a little bit, it's different than the traditional tensile strength because you want to pull the rock away instead of compress it. So this one's called Brazilian test. It's an indirect tensile strength test. You compress it of a rock discs. So this is just 1/4 of the rock. So the core sample is like this, and then we cut them into 4 quarters. Then we test each quarter at a time, and that's how you see you have 1, 2, 3, 4 sections of. So that's because we cut the sample into 4 pieces. Then you can see the different tensile strength at different locations of the core. Yeah. So how tensile strength are impacted during CO2 injection? Mostly, I'd say the changes are negligible. We don't see much change, except these data points, the red points that connected by those solid lines. So here it's lower on upstream and it's higher on the downstream. And they're all generally lower than the control sample, and these two are the control samples. At least the upstream part of the core, tensile strength appeared to be much lower. So that's the only, we would call significant decrease in tensile strength that we see. That all the other samples or all the other locations of the samples seeing almost no tensile strength weakening. Okay, I believe we went through all the static and dynamic measurements, observations. So to conclude, we think Marl-B sandstone, that's the formation that we're interested in for CO2 injection, was tested to be a highly robust reservoir with a low risk of mechanical degradation. And we also think the reservoir mechanical integrity is not impacted by CO2 injection in sandstones if there are non-reactive quartz overgrowth or reactive cements, if those cements and overgrowth are formed late in the diagenesis history, or if they're not load-bearing. And we also found that the CO2 inhibits the subcritical fracture, and mechanical weakening of the reservoir can be also prevented in this way. And that finding is consistent with the previous study. And last, the seismic velocity degradation during the injection may suggest loss of strength, but shouldn't be an indicator of how much the reservoir has been weakened. So we should focusing on the local change in rock texture, which you can tell those by looking at the static strength measurements, like tensile strength, uniaxial compressive strength, or the static Young's modulus measurements. So yeah, that's the whole part of the presentation, and these are the publications associated with this study. Any more questions? Thank you.
Thank you for the presentation. Yeah, I had a question on the first slides when you showed like how different parameters could affect the Young's modulus. The one before, I think.
Impact factor?
Yeah, this one, yeah. It seems this one shows that how this parameter affect each of the models, right?
Yes,
Uh,
yeah, and I have 11 models here.
Yeah, is there like experimental, something experimental related to that, to link between the experiments or the measured Young's models values and the different
Can you repeat your question again? Can you repeat
I
your
mean,
question?
you had like experiments to measure static Young's models, right?
Mm.
Is there any statistical analysis to show like their effect, like the individual effect of these parameters on this property?
Yes, yes. So these are the
Experimental.
models. Okay. I should say this. This model are the models that I showed you guys during yesterday
Yeah.
Brian's class. So those models are trained by those data. So we collect the data from on the samples first. So I would say these models are representative of the experimental data. Yes.
Okay. But since you mentioned the last yesterday presentation, I think we concluded that the surrogate model is the most preferred, right?
Yes. That's so in surrogate model here, the most impact factor is FGC over CC ratio. Interestingly, the porosity is not the most sensitive to that one. Yeah. But all the other deterministic model, they tend to have if we only consider a linear relationship, then porosity is the most important and most impactful. But the reality is it's not always linear. It's not always linear. So if we consider the two factors, linear and nonlinear, the chemical composition becomes more important than porosity, at least in that study. Yeah. So this part of the presentation just giving you idea of how important the role of porosity and chemicals composition of the sample on the flow through experiment. Yeah.
Can you explain a little further about the FGC?
So framework grain contents, it's a ratio, right? We did XRD analysis on that, so it's a ratio, and pretty much framework grains include quartz, feldspar, plagioclase, and then cement are the clays and carbonates, the sum of those, and that's how we calculate it.
So I actually have no idea about the carbon sequestration project. For example, for cement, you need to you need to apply cement to the underground rock.
No, the cements already exist within the rock,
Naturally, yeah.
Okay.
naturally formed. Yeah.
Okay, I thought
Yeah,
it was
not the
cement.
Yeah, not the cement in terms of engineering. No.
Okay. And so you are studying on the sandstone. For example, how about the granite? Can it be the host rock of the carbon sequestration reservoir?
So as far as I know, granite is not a popular storage host for CO2. Geothermal is quite popular, but not in CO2. So in CO2 sequestration mostly, right? Mostly people are considering saline aquifers, sandstone, depleted oil reservoirs, sandstone, or shale, and what else? Coal beds, or basalt, which is offshore. Those kind of. So granite would be. I think if you go to the DOE website, they list a bunch, and I don't think granite is one of it's not on the list. Yeah.
So the low permeability of the rock is not a necessary requirement for the reservoir of the carbon sequestration.
What is not requirement? What?
Because a granite has a low permeability, lower permeability than coal or shale or sandstone, right?
Yeah. So if you consider it this way, the capacity of granite might be low because of its impermeable property. Also, in terms of Yeah, mainly of that. I'm not sure about the reactivity of the minerals. They're mainly metamorphic, igneous, and could be reactive because basalt is also igneous rock, and then it can be really good. But basalt has a really large, not really large, like larger pore space than, so it makes a good host because it has good capacity.
Yeah, and for carbon sequestration project, if we inject the carbon CO2 underground, so how long can we store there? Did you consider the time dependence of the robustness of the reservoir? I mean the time. Did you consider the time?
Time?
I mean, if you inject the CO2 to the reservoir, there's a dissolution
Yeah.
that happens there.
Yeah.
So how long does it take to make the reservoir to very worse?
Yeah. So okay. So there are different trapping mechanisms. Here, what happened here in the lab? We're trying to simulate. Oh no, we're trying to recreate this mineral trapping thing. But mineral trapping in reality actually requires thousands of years to happen. It's a slow process. So if we want to know more about how long it will take effect, we'll bring these data into a simulation, let it run thousands of years or hundreds of years, and then pause it and then look at in thousands of years what will happen. So yeah, this process is a slow process. Yeah.
Okay.
You answered my question. You answered my quiz question. That's pretty nice.
Okay, thank you, Zhidi, for the great presentation.